All right, so we're going to talk about end behavior in the continuation of lesson 1.3. So the behavior of the graph of a function for very large values of x, either positive or negative, is commonly known as end behavior. It's what's happening on the far left and the far right side of my graph. So recall that the graph of polynomial resembles the graph of the power function for the highest powered term of the polynomial. So a few things to remember before we actually get into this is remember what x squared looks like. X squared is a quadratic, and if it's positive, it opens up, and if it's negative, it opens down. Okay? Any even-powered function is going to have the same end behavior as x squared. So if I have x to the fourth, it's going to have end behavior here. We don't know what's happening here in the middle, but we know the end behavior is going to be doing the same as x squared because it's an even function, okay? It's got that even exponent. And so if we had like negative x to the sixth, we don't know what's happening in the middle, but we know because it's negative and it's even, it's going to do the same thing as a negative x squared. Same thing when we're looking at the odd exponents, okay? We know that x to the first looks like this, and negative x to the first looks like that. Or we can say we know x cubed or negative x cubed, right? Notice the negative ones both go up to the left and down to the right. The positive ones both go down to the left and up to the right. They have the same end behavior. So even if I have x to the 51st, I know because that 51 is odd, its end behavior is going to be doing this because it was positive as well. All right, so we're going to use that to help us. So let's look at example 3. So state the power function that the graph of f resembles for very large values of x. Then find the end behavior for the function. Write your findings using limit notation. All right, so first thing is on A is look for the highest degree, and there it is. Okay, so this one's going to resemble y equals negative x squared. That's going to be our power function, okay? So we know what negative x squared looks like. It's going to open going downwards, right? We don't know how wide it is or anything like that. That's what this other piece of this graph over here tells us. We're not worried about that right now. We're talking about end behavior. What's happening over here and what's happening over here on those end sides. What's happening on the far left, what's happening on the far right. All right, so let's write this as a limit. So to write a limit, you're going to write limit, L-I-M, and underneath it you're going to say as x is approaching, and because we're talking about the far left and the far right, it's going to be either negative infinity for the left or positive infinity for the right. So on this one here, let's look at first as we're going to the left here, okay? So as we're going towards negative infinity, tell me about those y values. What's happening to the y values? Well, they're going down, and they're going to keep going down to negative infinity. And then we got to do the other side. So the limit as x goes to the right, it's going towards positive infinity. And we want to know what's happening to those y values. Well, as we go to the right here, notice my graph again is going down, and so my y values are going to keep going down to negative infinity. And so this is my limit notation. Now look at B. B says x minus 1 cubed. You can multiply that all out if you want to, but you don't have to. Because just remember, this means, I'm going to write it out, I'm not going to multiply it though, x minus 1 times x minus 1 times x minus 1. If I multiply all these x's, I'm going to get x cubed. So my power function is x cubed. Do you remember what it looks like? Well, it's odd and it's positive, so we know it's going to be looking something like this. Now, we don't know if it looks like this or if it looks like this, okay? We don't care at this point. We're only talking about the end behavior. This curve in here is caused by whatever we get when we multiply and we have that x squared, that x, and that constant, okay? We're talking about the end behavior. So we know on this graph looking at it that our limit as x goes to the left towards negative infinity, f of x equals, well, we can see as we're going to the left, our y's are going down, so negative infinity. And then the limit as x approaches the right, so towards positive infinity, as we go to the right, our y's are going up, so they're going towards positive infinity. Now C, I have to think a little bit about it, but we can see on C that it says we got the negative 1/2 x cubed times x. Well, if I multiply them, I'm going to get x to the fourth, and because this is negative, we know it's going to be a negative x to the fourth. Well, like we had said earlier, we know it's even, so it's going to follow just like what a quadratic would. And a negative quadratic would open downwards. So we know our graph is going to do something like this. We don't know what's happening in the middle. It could be W-shaped. It could just have a little slant. We don't know for sure, but we're just talking about the end behavior. So on this one, I have the limit as x goes towards negative infinity. And as I go towards the left there, I can see my graph is going down to negative infinity. And then we have the limit as x approaches positive infinity to the right. My graph is also going down to negative infinity. And then the last one here, again, we would distribute this through, but I would end up taking this times that, and that gives me 3x to the fifth. So my power function is just going to be a negative x to the fifth. Now, we know it's odd, so they're going to go in opposite directions, and it's negative, so it's going to do something like this. So when we go to write this, we can say our limit as x is approaching negative infinity, as we go to the left, that our y value is going to go up, so it's going positive infinity. And the limit as x approaches positive infinity on the right, we know it's going down to the right, so it's going to go towards negative infinity. All right, average rate of change. Well, what is a rate of change? If you remember back from Algebra 1, the rate of change is your slope, okay? So we're looking for the slope. But they call it the average rate of change because we're looking for the slope between 2 points of a nonlinear function. So let's read about it. It says a secant line is a line joining 2 points on a function. Finding the slope of the secant line through 2 points will give you the average rate of change over some interval a to b. You've known how to do this since your first algebra class. We just have new notation. In calculus, this notation is called the difference quotient of f at c. So we're just going to find the slope between the 2 points. Now, one of the differences is that usually when we get to the average rate of change, they're not going to give me the 2 points. They're going to give me an x1 and they're going to give me an x2, and I'm going to have an equation. Well, remember, anytime you know an x value in an equation, you can find that y value by plugging in that x value into the equation. So they told me here x1 is 1 and x2 is 3. So if I know that x1 is 1, I can find y1 because that's equal to f of that positive 1. And so they gave me the equation. They told me it was x cubed minus 3x, and we're going to plug in that positive 1. And we got negative 2. So I have the ordered pair 1, negative 2. They told me that my end point here, my x2 was 3. So I'm going to find y2 by plugging in that 3 into the equation. Oops. And I find that y2 is 18. So I also have the ordered pair 3, 18. And now if I want to find the average rate of change, we're just going to take our slope formula, y2 minus y1 over x2 minus x1. And so we said y2 was 18, minus y1 is negative 2, over x2 is 3, minus x1 is 1. So we get 20 over 2, which is 10. So our average rate of change is 10. Even though that x cubed minus 3x was not linear, we can still find the slope between the 2 points that it's looking at. All right. right, comparing functions and interpreting graphs. Now we turn our focus and attention to the comparison between two functions. Oftentimes, we want to find the y values where a function is positive, negative, or zeros. So example 5 says write a mathematical statement for functions f and g to represent verbal statements. Use function notation f of x and g of x as well as appropriate symbols, less than, greater than, I read that backwards, greater than, less than, or equal to. So it tells us a point x0 is located on the graph of f. Well, this is telling us that the y value is 0 when x is x. So we could write that as f of x equals 0, because remember, f of x is equal to y. Two functions, f and g, intersect at a given point. So if they intersect, that means they're equal. So we could say that f of x is equal to g of x. A point lies above the x-axis on the function g. Well, if it's above the x-axis, that means it's greater than 0. So we can say that g of x is greater than 0. A point lies below the x-axis on the function f. Below the x-axis means that y value would be negative, so it's going to be less than 0. The graph of f lies above the graph of g. Well, if f is above, that means f must be greater, so f of x is greater than g of x. Okay. The graph of f lies below the graph of g. So if it lies below it, that means it must be less than. So f of x is less than g of x. So then we have function operations with multiple representations. So example 6 here says, the graph of f of x and the table of values for the discrete function g of x are shown below. A says find the value of 3 times 2f of negative 3 minus 4g of 0. All right. So notice it's a graph of f and the table for g. So let's go through here. We have 3. Remember that bracket's just like a big parenthesis, okay? And it's 2 times, what is f of negative 3? Well, remember, this is f of x. So it tells us we're going to go to our f function, so that's the graph, and we're looking when x is negative 3. So when x is negative 3, I can see right there that the y value is 4. So we're going to replace that f of negative 3 with a 4. Minus 4 times g of 0. Well, that's g of x, so I'm looking for the y value when x is 0. So I'm going to come over here to the table. When x is 0, I find that the y value is negative 3. So we're going to plug that into the location there. And then we just need to simplify. So we got 3 times, 2 times 4 is 8. Negative 4 times negative 3 is positive 12. 3 times 8 plus 12 is 20, which gives us 60. So let's try B. It says given that h of x is equal to ax squared minus 4x, for what values of a is h of 3 equal to f of 2 minus g of negative 3? Well, let's see. It says h of 3 is equal to f of 2 minus g of negative 3. Whoops, sorry about that. All right, well, first I'm going to work on this side. We know h of 3, we can use this equation that they gave us up here, so I'm going to do that. So h of 3 is equal to a times 3 squared minus 4 times 3, which is what, 9a minus 12? And then we know that this is equal to f of 2, so I'm going to go back to my graph over here. And I'm going to go find f of 2. So on my f graph, when x is 2, what is its y value? 6. Minus g of negative 3. So go to the g table. When x is negative 3, y is 1. And so we got 9a minus 12 is equal to 6 minus 1. And then we can just solve this. So 9, I'm going to bring this over here. So 9a minus 12 equals 5. add the 12. So 9a equals 17, and divide by the 9. And so we get a is equal to 17 over 9. Then example 7 says use the graph of functions f of x and g of x shown at the right to answer the following. All right, so A says to find the domain of each function. So let's look at f. What you're labeling, guys, okay? So f is this graph right here. So I notice for when I look at the domain, remember we're looking for the x's, it keeps going down to the left and it's going up to the right, and I don't see any holes or any gaps or any of that in between it. So because it keeps going to the left, it keeps going to the right, there's no holes or anything in between, that means my domain is from negative infinity to positive infinity. Now it's a little low on mine, but on yours it says g of x down there, okay? So now look at g of x, that's the other graph. And so it's this one here, so I notice as I go along it, there's no holes, there's no jumps, it's continuous there. So therefore my domain is negative infinity to positive infinity as well. Now B says it wants us to find the values of x such that f of x equals 0. Remember, f of x is the same thing as y. So we're looking on the f graph where y is equal to 0. So I'm going to look where y is equal to 0, and I'm looking for the f graph. So I have it right there, and that's the only one, okay? So we would say at x equals, that's negative 9. Now below it, what you have written there, it says g of x equals 0. So this is saying on the g graph, where is y equal to 0? Well, we know y equals 0 right here still. And on the g graph, I see it's right here at negative 2, and it's right there at negative 6. So we'd say x equals negative 2 and x equals negative 6 for this one. All right, and so because I don't want to move my graph where I can't see it, I'm just going to write each one on the side, but you keep filling in your table. All right, so for C says to find the value such that f of x is equal to g of x. If they are equal, remember that means they're intersecting. And so we can see right here that it intersects there when x is negative 8. Let's see, it intersects here where x is a little bit more than 1, so how about 1.25? And it intersects right there where x is approximately 7. All right, D says to find the values of x such that f of x is greater than g of x. Remember, if it's greater than g of x, it's going to be above the g of x. Well, let's look. F of x is above the g of x right here. So we would say from where x is negative 8 to where we said x was 1.25. Now, would I use parentheses or brackets? There's no equal to in the problem, so always use parentheses, and that should have been positive, sorry. Is it above anywhere else? Well, here it dropped below, didn't it? But then it became above here, and it keeps staying above, so from 7 to infinity. Then E wants the values where f of x is less than g of x. And so if f of x is less than g of x, it's going to be below it now. So it's going to be all the places we didn't just use. So right here, so we could say from negative infinity to that negative 8. Over here where I scribbled this out, this is where it was below. So from negative 1.25 to 7. And that's it. So that's E. F said the value of x such that g of x is greater than 0. So if I'm looking for G, where I'm sorry, I'm on F, aren't I? F, where g of x is greater than 0, I'm looking for where the g function is above the x-axis. So find your g function. Notice it's above the x-axis right here. So that's going to be from negative infinity to -6. And then it drops down, and then it comes back up here, all of this, and it's going to cross somewhere over here, isn't it? So from -2 to maybe, let's say, approximately 12, because it goes off of our graph a little bit. All right, so let's see, we're on G. I want to know where f of x is less than 0. So that means I'm going to use my f graph, and I want to find where it's below the x-axis. So my f graph, and where it's below the x-axis, down here. So it's at negative infinity to -9. And, well, it doesn't go below it any further, does it? So that would be it. H wants to know the values of x, such as f of x increases. Remember, increases means it's going up. So I'm going to look for where f of x is going up as I read it from left to right. So I can see it's going up right here. So that would be, what, negative infinity to, what's that, -7. Then it goes down, then it goes back up right here. So from -4 to x is 0. Then it goes down and it goes back up here from where x is +4 to positive infinity. I wants to know the values of x such that g of x is constant. Remember, constant means it's not changing. So we're going to find that g of x where it's constant. And we can see that's from here to here, which is what, -1 to 3? J says the values of x such that g of x decreases. It decreases, that means it's going down. So we're looking for where g of x is going to decrease. And so we can see that's happening here from negative infinity to -6. See, and then it keeps going down even more, doesn't it? So I really should have went to -4. So let me change that to -4 because it's still decreasing. Even though it's at a different rate, it's still decreasing. And then we see that it was increasing there. And then we have our constant. And then it's decreasing again here, isn't it? So from 3 to positive infinity. K says the values of x such that f of x is greater than 0. Remember, if it's greater than 0, then it's going to be above the x-axis. So make sure you're looking at your f of x graph. And so f of x is above the x-axis right here. Well, all of it from there, right? So from -9 to infinity. And then finally L, so is where f of x decreases. So where it decreases is where it's going down. So read it from left to right. I can see it's going down right there from -7 to -4. And it's going down right here from x is 0 to x is 4. All right, guys, so that's all of 1.3. So